Every year, more than 17 million tons of massive concrete pipes are produced and buried deep underground, carrying the weight of entire cities above them. Without this enormous output, urban transportation and drainage systems would quickly grind to a halt. To manufacture reinforced concrete pipes, aggregates are processed and precisely measured. Steel is welded into cylindrical cages, and concrete is densely compacted inside molds. The finished pipes are then cured, inspected, and load tested before being buried beneath the ground. In this video, join Factron Process as we go inside the factory to see how powerful machines transform loose raw materials into the drainage systems hidden beneath modern cities. In Mohawk, New York, a concrete sewer pipe just 6 inches in diameter was installed in 1842. More than 180 years later, it is still in service, an extraordinary testament to the durability of a structure that appears so simple. Today, concrete pipes are found far beyond small city streets. They run beneath highways, airports, industrial zones, and heavily traveled transportation routes, quietly carrying stormwater and wastewater or channeling water beneath roadways. The scale of this hidden system is so vast that the EPA estimates the United States will require approximately $600 billion in wastewater and stormwater infrastructure investment over the next 20 years. These are no longer just isolated sewer lines. They form an underground network that operates continuously, keeping modern urban civilization from grinding to a halt. The journey of a concrete pipe begins with raw materials scattered across different locations. Limestone from quarries, clay beneath the ground, sand from extraction sites, and rough rock freshly cut from the mountainside. First comes Portland cement, the binding agent that locks the entire pipe wall into a single solid structure. Limestone and clay are crushed, blended, and fed into a rotary kiln heated to between 2,700 and 3,000 Fahrenheit. The intense heat transforms the mixture into clinker, which is then cooled and finely ground with gypsum to produce cement. Meanwhile, quarried rock is broken apart by a jaw crusher, reduced further by a cone crusher, and separated into different sizes by vibrating screens. Sand is also thoroughly washed to remove clay, dust, and other impurities. These aggregates form the largest portion of the mixture, typically accounting for 60 to 75% of the concrete's total volume. Once processing is complete, heavy dump trucks begin hauling the aggregates to the factory. A large articulated dump truck can carry around 35 tons of material per trip. At the same time, cement is transported in sealed tanker trucks, protecting the fine powder from moisture throughout the journey. As soon as the discharge gates open, sand and stone pour into weighing hoppers fitted with load cells, while a screw conveyor carries cement from the silo into a separate weighing chamber. Water and admixtures are also metered automatically, ensuring that every batch follows the programmed mix design. The mixer starts before the materials are loaded. A portion of the pre-measured water is sprayed into the mixing chamber first, followed by the aggregates and cement. Inside, steel paddles continuously fold, compress, and lift the material from the bottom upward. As the cement reacts with the water, it forms a binding paste that quickly coats every grain of sand and stone. Unlike the fluid concrete used on construction sites, concrete for pipe production typically has a water-to-binder ratio of only 30 to 38%. When the test mold is lifted, the concrete mass barely settles by even 1 inch, allowing the pipe to retain its shape immediately after demolding. To handle this zero-slump concrete, the mixer uses 2 motors, each rated at nearly 74 horsepower, while the actual mixing stage under standard test conditions may last only about 30 seconds. Once the mixture becomes uniform, the hydraulic discharge gate opens, releasing the entire batch onto a conveyor that carries it directly to the forming station. While the concrete is being prepared in the mixing area, a separate production line begins forming the steel reinforcement cage inside the pipe wall. Large steel coils are mounted on payoff stands, and the wire is drawn through a series of rollers to straighten it before being cut into bars of the required length. These bars are evenly spaced around a circular frame, forming the longitudinal reinforcement that runs along the length of the pipe. On larger machines, the system can position up to 60 longitudinal bars and produce cages nearly 23 feet long. Next, another steel wire is pulled from a coil and continuously wound around the longitudinal bars in a spiral pattern. At every intersection, a welding head presses the two wires firmly together and delivers an electrical current with a power rating of up to 125 kilovolts. Intense heat forms at the contact point, locking the wires into a strong joint without the need for welding rods. The steel cage rotates as it is gradually pushed out of the machine, while a stream of sparks flashes with every new spiral turn. Some production lines can manufacture cages up to approximately 17 feet in diameter, large enough for massive concrete pipes. At the end of the cycle, the machine expands one end of the cage to match the pipe's bell section. Workers then inspect its roundness, length, and welds before a crane lifts the entire reinforcement cage and transfers it to the mold assembly area. After leaving the welding machine, the reinforcement cage is lifted from its support frame by a crane and transferred to the forming area. Before installation, the steel mold is carefully cleaned. Any concrete left from the previous cycle is scraped away, the joint edges are inspected, and a thin layer of release agent is applied so the product will not stick when the mold is opened. Next, the base ring and the joint forming components are locked precisely into position. For pipes ranging from about 12 to 144 inches in diameter, even a slight misalignment can deform the bell end or cause a poor fit during installation on site. The steel cage is then suspended with a specialized lifting hook, distributing the load evenly along its entire length to prevent bending. Workers attach spacers around the frame before slowly lowering the cage into the center of the mold. Once the clearances are even, the outer mold is lowered into place, and mechanical pins and hydraulic locks tighten the entire mold assembly, ready to receive concrete. When the mold has been tightly locked, dry concrete from the mixer begins pouring from the hopper into the space around the reinforcement cage. This mixture almost does not flow on its own, so the steel distributing blades above must rotate continuously, sweeping the concrete into an even ring instead of allowing it to pile up in clumps. Just below, the packer head begins forming the pipe wall. Its rollers spin with force, pushing the concrete outward, pressing the mixture tightly against the steel mold and compacting it around the reinforcement cage. As more concrete continues to fall, the head slowly rises through the full height of the product, which can reach around 12 feet on some production lines. With every rotation, the stone particles are pressed closer together, trapped air is forced out, and the inner surface of the pipe becomes progressively smoother. The outer mold defines the outside shape, while the packer head determines the inner diameter. On larger machines, this process can produce pipes up to 84 inches wide. In just 5 minutes, a loose mixture is transformed into a solid, monolithic pipe, dense, reinforced, and ready for the moment of demolding. When the packer head completes its final rotation, the machine slows down and comes to a full stop. At this point, a scraper blade removes the excess concrete, while a pressing head levels the pipe opening before the mold locks are released one by one. Then, the steel mold is lifted straight upward, slowly sliding away from the concrete surface and revealing the freshly formed pipe underneath. Although the concrete is still soft, the pipe can stand on its own thanks to its low water content and the intense compaction force applied during forming. The massive concrete pipes are then moved into the moisture retention area. Mist spray systems, covering sheets, or steam are used to prevent the concrete from losing water too quickly. Once the concrete has reached sufficient strength, each pipe enters its final examination before leaving the factory. Technicians slowly inspect the entire surface, from the outer wall and inner barrel to both joint ends, looking for small cracks, voids, chipped edges, or uneven concrete left behind after demolding. Products with acceptable surfaces then move on to dimensional inspection. Their diameter, length, wall thickness, and roundness are checked with specialized measuring tools. Every deviation must remain within the allowed limits, because even a slightly inaccurate joint can cause an entire underground drainage line to leak after installation. After that, selected samples are placed into a 3-edge bearing test machine. A steel beam gradually presses down, forcing a 36-inch wide, 8-foot-long Class 3 pipe to withstand a load of up to about 32,400 pounds. Technicians monitor the first 0.01-inch crack to evaluate how the structure responds under extreme pressure. After passing the final test, each pipe is marked with its size, load class, and batch code before a crane moves it to the finished product yard. Here, the pipes are grouped by specification so the transport team can collect the correct products for each construction project. A typical pipe section is about 8 to 12 feet long, while larger models can weigh more than 10,000 pounds. For that reason, every movement must be slow and precise. Even a single impact on the bell end can damage the joint, so the pipes are placed on support blocks and kept safely separated from one another. When the truck arrives, the crane lifts each section onto the trailer one by one. Blocking wedges keep the pipes from rolling, while tie-down straps secure the entire load firmly in place. From here, the product leaves the factory, carrying the combined weight of steel, stone, and concrete to the place where it will serve for decades. After leaving the factory, the heavy concrete pipe sections are transported to the construction site for installation. Before lifting begins, workers inspect the pipe body, both joint ends, the lifting cables, and the locking hardware to make sure no cracks or damage have been missed. At the same time, an excavator opens the trench along the designed alignment. Its steel bucket digs deep into the ground, forming a straight channel where the pipe will be placed. Once the required elevation is reached, a vibratory roller compacts the trench bottom. If the soil is soft or unstable, the weak material is removed and replaced with crushed stone or gravel. Finally, dump trucks pour small aggregate into the trench, and the excavator spreads it into a bedding layer about 6 inches thick, creating a stable base for the first pipe section. When the bedding layer is ready, the crane slowly lifts each pipe section off the truck and lowers it into the trench. The bell end is positioned toward the higher side of the line, while the spigot end faces the lower side, allowing water to flow smoothly through the system. Before joining the sections, workers use a stiff brush to clean away soil, sand, and loose concrete from both joint ends. A rubber gasket is then fitted evenly around the spigot end. Next, a layer of specialized lubricant is applied to the spigot and the contact surface, helping the two pipe sections slide together smoothly without twisting, rolling, or dislodging the gasket from its groove. The crane keeps the pipe section close to the bedding surface, while workers below signal the operator to shift it left, right, or lower it little by little. Once the spigot is perfectly aligned with the bell end, the excavator slowly pushes the two pipe sections together. At the same time, workers watch the joint from all sides to make sure the gasket has not twisted and the concrete edges have not been chipped by impact. When the spigot reaches its final position, they inspect the entire joint gap once again. Only when the two pipe sections close evenly and sit firmly on the bedding layer are the lifting cables removed, allowing the crew to continue installing the next section. Once the joint is secure, the excavator begins placing crushed stone along both sides of the pipe body. Workers use shovels to pull the material into the lower haunch areas, and then a compactor moves along each side to tighten the stone around the pipe. The material is spread in thin layers, about 4 inches at a time, and compacted alternately on both sides. This method keeps the pipe from shifting out of alignment while creating a firm soil structure that works together with the concrete to carry the load from above. Once the backfill rises above the top of the pipe, the excavator continues adding soil until a cover layer about 2 feet thick is formed. Only then are heavy machines allowed to pass overhead without placing direct pressure on the pipe body. Finally, a vibratory roller compacts the remaining trench before the stone base and road surface are restored. From this point on, the entire pipeline disappears beneath the ground and begins its decades-long job of carrying water. From stone, sand, cement, and steel, the production line has created pipes strong enough to sit deep underground, carry continuous water flow, and withstand the heavy traffic loads above. But that strength does not come only from their massive size or thick concrete walls. It comes from the precision built into every single stage of the process. The steel cage must be perfectly centered so the pipe can carry force evenly around its wall. The concrete must be tightly compacted so no hidden voids remain inside. The joint must close evenly to prevent leakage, and the backfill on both sides must be firmly compacted to keep the pipe stable for years underground. Once the road surface is restored, the entire system almost disappears from view. Only when heavy rain arrives does the role of these massive concrete pipes become truly visible. Water is carried away silently below, while vehicles, buildings, and daily life continue normally above. Behind that hidden structure are machines, calculations, and precise human operations that most people never get to see. Leave a like and subscribe to Factron Process as we continue exploring the massive industrial processes that quietly keep the world moving.